Going through the book, 50 Challenging Problems in Probability, and this is question 13. I actually skipped questions number 10, 11, and 12 because I didn't feel like they were that interesting, and I didn't really feel like they were good enough problems to do videos on. They're pretty subjective, but the book is linked down below, and if you want to try 10, 11, and 12, be my guest. You'll probably understand why I didn't make videos on them, but this problem is called the prisoner's dilemma. So 3 prisoners, A, B, and C, with apparently equally good records have applied for parole. The parole board has decided to release 2 of the 3, and the prisoners know this, but not which 2. A warden friend of prisoner A knows who's going to be released. Prisoner A realizes that it would be unethical to ask the warden if he himself is going to be released, but thinks of asking for the name of one prisoner other than himself who's to be released. He thinks that before he asks, his chances of release are 2/3. He thinks that if the warden says B, his own chances have now gone down to 1/2 because either A and B or B and C are to be released. So A decides not to reduce his chances by asking. However, A is mistaken in this calculation. Explain. I think the biggest misconception for A is the shrinking of the sample space. So initially there are 3 equally likely possibilities, but if the warden says B, then there are only 2 possibilities, and prisoner A believes these 2 possibilities, A, B, and B, C, are equally likely, and they're not. And I'm going to show that right now. So let's define some events. Let's call S to be the event where the warden says B in response to A's question. And then we have our 3 pairings, which are equally likely, so each of them are 1/3 probability. A, B, A, C, and B, C. Let's calculate the probability that the warden says B. So if the actual release pair is A, B, the warden will say B 100% of the time, because prisoner A asks the person to be released other than himself, right? And if the pairing is A, B, then the only other person to be released other than himself is B, so he has to say B. He's forced to say B. So what happens with probability 1? Now moving down, if the release pair is AC, the warden can't say B, right? B isn't in the release pair, so he just say C. So the warden says B, the probability is 0 in that case. And then if the release pair is BC, the warden can either say B or say C, so he says B like with the flip of a coin, right? He says it 1/2 of the time. So when we calculate these joint probabilities, the probability that warden says B and it's AB, right, is 1/3. The probability that warden says B and it's AC is 0. And the probability that warden says B and it's BC is 1/6. And when we sum those probabilities up, we get the total probability that the warden says B to be 1/2. So the warden says B 1/2 of the time. And we want to know what is the probability that A will be released if the warden says B. So right here is our probability of interest. And let's really think about this event. The event that A will be released given the warden says B is the same thing as the event that AB is the release pair given the warden says B. Because there are 2 events that A is released in, AB and AC. Once the warden says B, AC is impossible anymore. So the only possible event is AB. And this is what we're computing. AB given S sub B, right? We can just use our elementary conditional probability formula. And because we've already computed these 2 probabilities up here and up here, we know that this is just 1/3 over 1/2, and that equals 2/3. So his belief is wrong that his chances go down to 1/2. His chances stay at 2/3, because when the sample space shrinks, both the events aren't equally likely. Thank you.